So hi everyone, my name's Liam and I'm going to be presenting hopefully a brief introduction to nucleon form factors in lattice QCD. And I'm giving this as sort of an introductory sort of presentation for the lattice gauge theory for high energy physics class aimed at looking at form factors on the lattice. So I've got just a bit of an outline of what I'd like to talk about. And so I'll start with, defining what form factors are in the context of hadrons. I'll be focusing on the nucleon form factors, and I'll really be focused on giving an example, essentially, of the electric and magnetic form factors. And then I'll talk a bit about what these form factors can tell us about the properties and structure of the nucleon. And I'll also very briefly touch on the axial form factor, since that's another kind of form factor that one might be interested in studying. I'll then talk about how we actually calculate these form factors in a typical lattice calculation. I'll sort of recap some things that you would have seen in previous classes, looking at fitting matrix elements to correlation functions. So we won't go into too much detail on that. But then there's some extra steps we'll need to take in order to connect these matrix elements to those form factors, and namely solving some overdetermined systems of equations and other considerations. And then after that, once we know how to extract the form factors, the typical thing one does is to parameterize their momentum transfer dependence, and calculate things like the radius of say the proton. And then I'll finish with some closing remarks. So to start, what are form factors? So we could imagine, say, an elastic scattering process where we have a photon, for example, which scatters off a nucleon, say a proton or neutron. And we're supposing that that photon has enough energy that it can resolve the internal structure of the nucleon in the form of quarks and gluons, or we might call them partons. But it lacks the energy that we find in, say, a deep inelastic scattering process. So the proton isn't being smashed up into many pieces in this scattering. This is just elastic scattering. We could then think about sort of writing down the most general form for that interaction vertex. And it turns out this will hold to all orders in perturbation theory as the following. So we have on the left here a little cartoon of a sort of a segment of a Feynman diagram where we have a nucleon, say like a proton, which is coming in with some initial momentum p and being sort of probed by a photon represented by this squiggly line, which imparts some momentum transfer q, leaving the intact proton to scatter off with some final momentum p primed. So we can write down that vertex in terms of this matrix element, where the photon is carrying this vector current v, which, if we're sort of imagining this photon impacting one of the quarks in the proton, it's we can write down that vector current in this form here, this q bar gamma mu q. So we have sort of this matrix element on the left here, and we know that it should transform as a vector. So we could think about firstly writing down the spinors corresponding to that proton having final and initial momentum p primed and p, and then between those we can write down all possible sort of structures which transform as Lorentz 4 vectors. So we could have something involving a gamma mu, a q mu, a p mu, or a p primed mu. Those are all the 4 vectors we have to work with. And those are accompanied by some factors, these F1, 2, 3, and 4. Now, I won't go through all the details, but essentially you can manipulate these and use things like the Ward identities to reduce these 4 terms down to just 2. There's a structure involving a gamma mu and then something involving a sigma mu nu q nu. And these come with the accompanying form factors F1 and F2. So this is how we sort of derive the Dirac and Pauli form factors. But this sort of argument holds in other cases as well, and we could just sort of understand this is just an example of saying that form factors parameterize the sort of these all orders hadron probe vertices that we see in elastic scattering, if we're talking about hadron form factors, that is. Now, I've just talked about how we end up with the Dirac and Pauli form factors, but we could just as well work with another set of form factors which are analogous, known as the Sachs form factors, the electric and magnetic form factors GE and GM, which are just related to F1 and F2 by these relations here. And I'm introducing this capital Q squared notation here, which you'll see quite often. It's just minus lowercase q squared. And there's benefits to working with one set of form factors over the other. There's particular things you might want to study with one set of form factors and not the others, which we'll touch on later. But just to get a sense of how we can obtain these form factors, sort of the first way one might think of doing this is by performing some electron-proton scattering experiments, and then making use of something like this, the Rosenbluth formula, which relates a cross-section which we can measure to various other quantities we can measure, such as the energy of the outgoing and ingoing electron to this process. It's the electron scattering angle of the proton, and then some other sort of kinematic factors, this tau and this epsilon, and then the form factors that we want, the GE and GM. And so that's one way we could obtain the form factors, by performing some scattering experiments. Once we have them, they can tell us a number of things. So I've just picked out a couple examples and tried to relate them as well to things that you would have seen before. So for example, in a previous class, you would have looked at extracting the charge of the nucleon, the vector charge of the nucleon. And so that's actually given by the form factors F1 and GE at this momentum transfer Q squared equals 0. This case that you've looked at before is really just a specific case of one of these form factor analyses. Similarly, we can get information about, say, the anomalous magnetic moment of the proton, for example, from F2. And actually, if we just look at GE and GM, they can tell us a bit about the electric and magnetic field densities within the hadron. They end up being something close to the Fourier transforms of these densities. Another thing that's of interest for many people in the community is that, well, there's a lot of people studying these sort of higher level structure functions known as parton distribution functions and generalized parton distribution functions, PDFs and GPDs. And the form factors provide some constraints on these structure functions. And so those are useful for the large number of people and the growing number of experiments that are aimed at studying these particular quantities, say at Jefferson Lab and the upcoming EIC. Another big reason that we would be interested in studying the form factors is that we can actually extract the size of the proton from its form factors. And so I've just got the formula here, but I'll touch on it again later, that this mean square radius of the proton with respect to its electric or magnetic fields can be determined from taking the derivative of either GE or GM and evaluated at 0 momentum transfer. So that's an important quantity for fundamental physics that we might want to know. And so people have determined this experimentally for many years. And I wanted to point out that this actually led to something called the proton radius puzzle. So there were three sort of main approaches that people used for obtaining the proton radius from the form factors. And that's electron-proton scattering experiments, or experiments shining a laser on hydrogen and performing spectroscopy, or looking at Lamb shifts from muonic hydrogen. And depending which experiments one conducted, one found quite different results for many years. So in this plot on the right, I'm showing, it's a summary plot that I've borrowed that shows the results from many different types of experiments in determining the proton's charge radius. And we can see in particular this CODATA result, this 2014 result, which is essentially an average of various electron-proton and electron-proton scattering and hydrogen spectroscopy results to form this sort of world average. And then that differs quite significantly from the results one gets from muonic hydrogen experiments, shown by this orange band here. So that tension was, a source of, a bit of concern about a particle we should know a lot about, the proton. And so it really drove a lot of interest in many areas, including in lattice QCD, in studying the form factors and obtaining an estimate of the radius. I will just note that this puzzle is close to being resolved. The most up-to-date CODATA result has been revised down to something much more in line with what you see from muonic hydrogen experiments. But nevertheless, this is still, a good opportunity to benchmark our lattice calculations and see what they tell us about this important quantity. I also just wanted to include a slide here about the axial form factors. So these are another kind of form factor we could imagine rather than a photon interacting with a proton, say a neutrino, so a weakly interacting particle scattering off this nucleon. And so that will carry a different kind of current, an axial current. So we'll have a gamma mu, gamma 5. And so we can parameterize the corresponding interaction vertex in terms of some different form factors, in this case, the axial form factor GA and the induced pseudoscalar form factor FP. And so then, we could go and study these in much the same way as we would for say, the Sachs form factors. Now, while the axial charge GA, but lowercase GA, is quite well known from experiments, very precisely known, the same cannot be said for the axial form factor at non-zero Q squared. And so that's a real opportunity then for lattice QCD to have some input, since this is, an important quantity for studying things like CP violating phases of neutrinos, neutrino mass hierarchy and oscillations. So these very important sort of pushes in the community to understand these quantities, and lattice can really help pull down these uncertainties on the axial form factor. I won't talk too much more about that. We'll really focus on just the electric and magnetic form factors here, but I've included a link just to a helpful review on this topic. So now I want to go through essentially how we will perform our analysis of the form factors from the lattice perspective. And so I'm going to start assuming that we understand how to do this with charges. But here I'll just very briefly recap the procedure and sort of draw analogs between what you would have seen when analyzing charges and what we need to do slightly differently for the form factors. So we start assuming that we have a set of correlation functions, 2-point, 3-point correlation functions or correlators. And if we start with just the 2-point correlator, we imagine that as, say, a nucleon being created at a source at some space-time point and then allowed to propagate across the lattice and annihilated at the sink at some later space-time point. Oh, this is a typo, sorry. This nucleon has, the same momentum and spin as it propagates across the lattice. It's just one momentum for the 2-point correlators and one spin. But we can write that correlator in terms of essentially these vacuum expectation values, where we've got interpolating fields creating and annihilating our nucleon at the source and sink. There's some Dirac indices which we project with an appropriate Dirac gamma projection operator to pick out, say, the spin half positive parity nucleon, if that's what we're interested in studying. And then we also need to perform some projection onto that that momentum that we're interested in studying. Similarly, we can look at the 3-point correlators. It's the same picture, where now we have some operator O, might be a photon, for example, which imparts some momentum transfer. So now this nucleon has different ingoing and outgoing momenta in the 3-point correlator picture, and we can write down the corresponding expression for that 3-point correlator. Now, again, I'll just recall from your previous classes that we can insert complete sets of states, and manipulate these definitions of the correlators to realize them in terms of towers of exponentials. So we have this sum of exponentially decaying terms for the 2-point correlator, and a similar sum over decaying exponentials with these matrix elements for the 3-point correlators. Now, just as you would have done in the previous classes, we want to perform fits to the correlators. So we take these expressions and truncate them to some finite number of terms. We might take, say, a 2-state fit for which the corresponding expressions for the 2-point and 3-point correlators are given below. And these are things that hopefully you've seen before. The thing just to highlight again is that the quantity that we're really interested in is this ground state matrix element. So this thing I'm labeling Mij, it's M00 that we are really interested in. And this is just the same as what we would have seen for studying charges. So yeah, just as you would have done for charges, we perform fits to those correlators. But now there's some important things that I just wanted to point out that distinguish this from the previous case. So now the important thing is that we have non-zero momentum transfer. So there are some simplifications that one could make. If we go back to the previous slide, looking at our 4 matrix elements, it turns out that the M01 and M10 they obey some symmetry when you have the same ingoing and outgoing momenta on your states I and J. And so what that allows you to do when looking at charges is make this simplification that those matrix elements are equal. That's not the case here. So you actually, in principle, need to fit all 4 matrix elements. So that's something I just wanted to point out, as it might be something that people had done in the previous case, which won't work here. But then, there are other things we do. We once we perform the fits, we construct effective mass plots and use those to monitor our 2-point correlator fits. We then also want to construct ratio plots to monitor our 3-point correlator fits. Now, we're going to do exactly that here, except if we compare with what you would have seen when looking at charges, you would have had essentially a ratio comprised of just these terms, like these first numerator and denominator inside the square root here. That's what you would have had for the case where P equals P prime. But now, to explicitly take into account that non-zero momentum transfer, you need to construct this sort of modified ratio, this more complicated ratio. But it works exactly the same. All the functions and techniques you developed in the previous classes will work for this as well. But once you've constructed that ratio, you can think about taking the large time separation limits as you would have before, and realize that if you plug in your expressions for your correlators, that your fit forms for the correlators, then in the limit of large time separations, this entire expression just reduces down to this M00. And so this limit that we're taking is what I'll label with a calligraphic R here. And so here I just want to include some things that hopefully people are somewhat familiar with. So there's just a typical effective mass plot on the left. So these are things that you should know how to produce. And then on the right, this is a ratio plot like you would have produced when looking at charges. But I picked this plot because now we've got this non-zero momentum transfer. There's one unit of momentum transfer in the y and one in the z directions. And so that leads to this characteristic feature of having like a non-symmetric ratio plot. When you looked at charges, the plots would have all been symmetric, but here that's not the case. So that's something that if you see that when you're making your plots, don't be worried. That's a feature, not a bug. Now, sort of pushing forward in the calculation, what we will need to do is then connect these matrix elements that we've extracted from our fits to the form factors that we are trying to solve for. So if we think about that that ratio of correlation functions, if instead of plugging in the fit forms of the correlators, those two-state fit forms, if we actually plug in the full definition of the correlators and reduce those down to traces, you'll end up with expressions like these. And this gamma O here is going to be replaced by the particular operator that you're working with. So if that's if I go back a couple slides, if that's the vector form factors that we're looking at, that's going to be our expression involving F1 and F2 with these gamma matrix structures. So that will appear in this expression where I've labeled this capital gamma O here. If you so I'm trying not to go into too many details here, but if you plug that in and then compute evaluate these traces, you actually end up with relations between these large time limits of the ratio, so these ground state matrix elements, and your form factors. And so some examples here are given. So I've given them for the Dirac and Pauli form factors, F1 and F2. So here I've broken them up into the cases where we have different Lorentz indices. So the I here is Lorentz index 1 or 2, so the X or Y Lorentz index on our vector current. And then there's also another relevant expression is when the Lorentz index is 4, it's the temporal component of the current. And so these matrix elements that you obtain from fits to the corresponding correlators can be related through these kinematic factors to our form factors F1 and F2. And this is at at each Q squared, right? We have one of these equations. And analogously, we could work with the Sachs form factors and derive similar expressions. Those are given below. And I'll just point out, so here in the case of F1 and F2, you just have the real components of the correlators contributing. But for one of these sets of expressions for GE, you actually need the imaginary component. So that's just something to be slightly aware of. But yeah, all of the all of the sort of parts of these relations are things that we have from our fits. So our M sub n is just the mass of the nucleon, so you can get that from your 2-point correlator fits. And similarly for this EP, which is what I'm relabeling this E0 at P. So a ground state energy at the momentum P. So those are things you can get from your fits, and then you can just plug in your whatever momentum values are needed to relate your form matrix elements to your form factors. Now, these equations that we've obtained sort of need a bit of work in order to solve. So I sort of said, we've got these equations now, we want to solve for the form factors, but there's some important considerations that we need to take. So those formulas I showed on the previous slide, they're of this kind of form, where you have your ground state matrix elements on the left being related to your form factors up to some kinematic factors. Now here I'm introducing some different subscripts. So so start with I. So I is just the label for each form factor. So if I go back a slide, so here if we're looking at F1, F2, our I is going to be 1 or 2. Or it might be if it's GE, GM, I is E or M. Then K here are the different kinematic factors that sit in front of the form factors. The alpha label, though, is important because it is distinguishing, firstly, the Lorentz index that we're looking at. I already spoke about how those equations have been separated based on Lorentz index. But actually within each of those cases, we also have a set of equations for each momentum. So really, if you write down the equations for a given q squared, you could imagine, let's say you have a q squared of one unit of momentum being transferred in any along any axis, right? So there's 3 directions that momentum could be transferred along, and like 3 axes it could be transferred along, and then for each of those you have 2 directions, right? Plus or minus 1, right? So what this means is that for a given q squared we have many equations which can enter, and so really you have a system of overdetermined equations. You have more equations than you have unknowns at a given value of q squared that you're trying to solve these form factors for. Not only because of the momentum, but you also have the additional Lorentz index to worry about as well. So we can't just sort of solve this as like a 2x2 system of equations or something like that. In principle, what we should do is perform a fit to all these relations, all the relevant ones at the given q squared, and minimize this chi-squared, where we have the covariance matrix, which says the covariance matrix of our matrix element estimates. But there's a thing that happens, unfortunately, when performing such a fit. When you compute this covariance matrix, quite often it will have a very large condition number. So it'll have very large. It may have a large condition number, and which means it may have very large eigenvalues. And so when you take the inverse, it can be sort of ill-determined. You can run into instabilities in determining that inverse, which will throw off your fitting. So a common way of getting around this is to use something called shrinkage. I guess if people have questions, they can ask during the class. I won't go into more detail on that, but there are ways to get around this. Alternatively, what we might think about doing is to simplify the problem a little bit. So we might only use, say, a subset of these relations, depending which Lorentz components you look at. Some may have more noise than others, so you may not consider them. Or there may be some symmetry you're able to exploit where you can perform an average over some equations which essentially contain the same information. So there are some tricks you might be able to use to get around this issue. But in any case, this is sort of the rough blueprint of how one would want to solve for the form factors. Once we've done that at each of our different momentum transfers, then the next step really is to parameterize their q squared dependence. And so historically, this was done using dipole forms. So that's something like what I've shown here. And this, it was used for a long time because it just sort of worked. When looking at experimental data, they look like they follow a dipole, and when you fit them with a dipole, it reproduces the data very well. But the more sort of model agnostic thing to do is to do something called a Z expansion fit. So that's where you write down a polynomial expansion in this quantity Z, which is defined like this. I won't go into too much detail here because the video will be too long, but you'll be able to explore this fitting parameterization in the class. But essentially, this takes into account some branch cuts for your form factors, and you can choose this T naught. Usually, that's chosen to be 0. That simplifies the sort of calculation a little bit, but you don't have to. There are some ways you can determine the optimal value of T naught. But essentially, you can write down this polynomial expansion and perform a fit up to some order, which we label as Kmax in this quantity Z. But once you've performed those fits, however you choose to do it, you are then able to extract things like the electric and magnetic radius of say the proton. So you take your form factors GE or GM, and you can Taylor expand those in terms of this mean squared radius, r squared. And then you could think about trying to isolate that quantity, and you could do that by taking firstly a derivative with respect to q squared. So it'll kill off this first term, and then you could evaluate that at q squared equals 0, leaving you with just that just this term here, and then rearrange that for your r squared, your radius of the proton, your electric or magnetic radius, depending which form factor you're using. And so putting that all together, we could look at some example results of what you'll hopefully produce something similar to in this class. So here firstly, the data points show our results at each different value of q squared written in physical units. For the form factors GE and GM, just noting that those have been divided by the vector charge to renormalize them. And so having done that, we perform a fit to them. So in this example, I show a Z expansion fit with a Kmax of 4. And so that's shown by the blue line and the blue bands. And then the final thing we might want to do, since we can readily renormalize these form factors just by dividing by the charge, we could then go and compare with other lattice results or with phenomenology. Here, this dashed line is sort of a classic point of comparison. This Arrington result for the form factors from phenomenology. And so that's the kind of results we would be looking to be able to produce after this class. And so finally, I just wanted to finish with a couple more points of motivation to maybe give you things to think about, or the things you might be interested in looking into when it comes to looking at the form factors. So there are some open questions around things like the large q squared behavior of the form factors. For example, the ratio of the Sachs form factors GE and GM for the proton. Those are expected to cross through 0 based on experiment at around 8 GeV squared or perhaps higher. So that's shown by these different colored data points in this plot here. We can see that at around 8 GeV squared, there's no possibility of the form factors crossing through 0. When it comes to F1 and F2, if we look at their ratio at large q squared, there's questions about well, that's expected to have some logarithmic behavior based on perturbative QCD arguments. And so the question is, okay, where do those arguments sort of start to take hold? Where does the onset of perturbative QCD set in? So that's another reason to study form factors at large q squared. I've already talked about, if we're studying the radii, we're interested in small q squared. So they're interesting across the whole range of values of momentum transfer. And then another point is that there are other ways of studying QCD using different models to describe it, such as vector meson dominance models, Dyson-Schwinger equations, constituent Clark models, and those will give us different expectations for the form factors, and those have sort of been depicted as the different colored and different patterned lines in this plot. And we can see that while they agree fairly well in the region where we have plentiful data, in the region where data is scarce and going beyond that, these models start to diverge and have very different expectations. And so having input from the lattice on these form factors can help hopefully get some understanding about these models as well. And then just a final point, just on the actual form factors this time. These, for a long time, there was tension between the results from lattice and with experiment, but it turned out that this can be resolved by essentially correctly identifying or being more careful identifying excited state contamination, and in particular these pion-nucleon multihadron sort of states that can play a dominant role in these processes. And so these kinds of considerations are kind of pushing the field forward in needing to study, say, the axial form factors with multi-hadron operators, not just these simple like operators coupling to nucleons. So with that, I'll finish, and I'll see you at class.